This is a really nice problem. We have a bobsled that starts from rest on this hill at point A, and it goes down the track, and then it encounters this patch of friction, then it goes around this loop-de-loop. And we're supposed to figure out the maximum length of this friction patch so that the bobsled will still make it around the loop without losing contact with the track. So the first thing to figure out is, what does it mean without losing contact with the track? Because that's the requirement that we need to meet. So if the bobsled comes in too slow, it could not make it up this loop at all, or it could come around to the top and lose contact at the very top and fall down. And that's the minimum. If it can clear the top without falling off, without losing contact, that's the minimum requirement. So that corresponds to the normal force going to zero at the top of the track. And we've done that a lot when we were doing like fan clan problems and stuff like that, F equals ma. Okay, so we want to use F equals ma at this point. So at that point, if we draw a free body diagram, normally we would have the gravitational force pointing down and the normal force also pointing down, but the normal force has gone to zero, so we just have Fg. So if we were to sum the force in the y direction at this point, it would be equal to the mass times the acceleration in the y direction. So if we define our positive y to be down, this would just be Fg, no other forces, but it is accelerating because it's moving in a curve. So the acceleration would be m v squared over the radius of the circle. So Fg is mg, so mg equals m v squared over r. These m's cancel out, and we can solve for v. V is the square root of g times r. So that's the speed that the car needs to have at the top of the track in order to make it around. So I'll just make a little note that this is the minimum speed at the top of the loop. Okay, so now we know the speed. So what's going to determine that speed? Well, the amount of mechanical energy that the bobsled has left after it goes through this patch of friction is going to determine the speed at the top of the loop. So what's happening here is the roller coaster goes down this hill here and encounters this friction patch, and the friction patch is going to steal mechanical energy away from the bobsled and convert it into heat. So let's look at the energy at 3 points. Point A, let's say point B is here right after the friction patch, and let's call this point C. So at point A, the mechanical energy in the system, E-mech, is going to be all potential energy because it's starting from rest. So the potential energy at point A is mg times this height. So how much mechanical energy is at point B? It has to be less than it was at A because some of the energy has gone into heat. And the amount that's gone into heat has the magnitude of the work done by friction on the bobsled. So the work done by friction on the bobsled is the force of friction dotted with the displacement. So the force is mu times the normal force, and the displacement is L. And these two forces, so the force is backwards, and the displacement is in this direction. So this dot product should be negative. So we have mu and L, and in this case, because the only forces acting in the y direction are the normal force and gravity, the normal force is equal to mg in this case. So this is minus mu mgl. So the work done by friction is negative, which means it's subtracting from the mechanical energy. So the mechanical energy at point B has to be equal to the mechanical energy at point A minus mu mgl, because we need less energy afterwards. So this will be mgh minus mu mgl. So if L is 0, if there's no friction patch, the energy at A is just the energy that we had at B. Okay, so that's the energy at B. Now, how about the energy at C? So between B and C, there's no friction. We have all conservative forces, so mechanical energy between points B and C is going to be conserved. So all we have to do is take the mechanical energy at B and set it equal to the mechanical energy at C. So B we just found, so we can plug that in. And now we'll look at point C and ask what kinds of energy it has at that point. So it's moving, it has a speed v at that point. So it has kinetic energy. It also has potential energy because it's at this height. So we have to add the potential energy mg to h over 3. And does it have anything else? No, just kinetic and potential. Okay, great. So all we have to do now is substitute this v in here. And what is r? R is 1/2 of this height. So that is h over 3. So v is the square root of g times h over 3. Okay, so here we can actually, let's plug it in first. So we have mgh minus mu mgl is 1/2 m v squared is gh over 3 plus mg times 2h over 3. So now the only thing we have to do is solve for what we want, which is L. So we can see here that mg is going to cancel from every term. So h minus mu L is h over 6 plus 2h over 3. So 2h over 3 is 4h over 6. So this whole side is 5h over 6. So if I just rewrite that real quick, h minus mu L equals 5h over 6. So I'll move this to the other side and that to the other side. So we'll get h minus 5h over 6 equals mu times L. This is h over 6. So L is h over 6 mu. And that's it.